Okay, question 4H6 from Statistical Rethinking, second edition. Before you run any of this code, make sure that you've installed and loaded the Rethinking package with these two blocks of code here at the top of the Colab sheet. Let's see. We want 4H6. Okay. So we are returning to the cherry blossoms data again, and with this question, so we just, in 4H5 we used the cherry blossom data, and in 4M8 we used the cherry blossoms data. And in this question, we're being asked to modify the priors on the W parameter and see what this does to the prior predictive distribution. So let's go through that. So I've gone through this code, or very similar code, for both 4H5 and 4M8. So look at those for a little bit more detail, but we'll go through it very quickly here. So first I'm going to load the data, cherry blossoms, which is in the Rethinking package, and I'm going to give it the object name D. And then I'm just going to look at the complete cases for a variable in that data frame called DOY, which is the day of the year at which cherry blossoms bloom, the first blooming. Okay. And we're going to create splines, and again, I've covered that already, and so I won't go through that really in depth here, but we're going to have 15 knots, and we're going to place them according to this code here, just kind of equally distributed from across the span of years, and it's going to be a third degree, a cubic polynomial spline or a transition at each knot. Okay, and so here's our model, and we'll look at what the prior predictive distribution is of this model. But just to go through everything, DOY is being modeled as a normally distributed variable with mean mu, sigma, or standard deviation sigma, and mu we are regressing on an intercept with this prior distribution here. Okay. As well as on B, and B again is just the splines that we created. Again, look at the previous videos for a little bit more detail about what B looks like. So, and then we are estimating the parameters for W, and again, W is the value by which we are multiplying each value of B by in order for our estimated curve to fit the data well. Okay. Yeah, so then we're not going to look at the posterior of this. We're going to look at the prior distribution. So this model expects certain things before seeing the data, our prior. And so to look at the prior, first we're going to extract the prior with this convenience function out of the Rethinking package. Okay, and then we are going to use these commands here, the link and the apply commands, to look at the value of the mean value at each x value or a year, so the most expected value of DOY at each part of the year, as well as a credibility interval around that expected value, and we'll plot it here. So let's go ahead and do that. Run the code. Okay. So again, what we see here is not the posterior distribution, but rather the prior distribution. Okay. And we've done this in a couple of ways. So first of all, these blue dots are the actual data points across the year. So each data point, there's one data point roughly for each year. Not all years are included in the data set, but roughly every year has a data point. And its Y value is the day of the year at which these cherry blossoms are blooming. Okay. Now, in the middle, there's a dark line there that's being kind of confiscated by quite a few different layers here. But this is the most expected value, I guess we'll call it that, the most expected value at each time of or for each year for DOY, right? And notice it's a very flat line. It just goes straight across. So in other words, a priori, our model really doesn't expect the DOY to change across time. Okay, of course the data can update this, but a priori that's the most expected likely value, right? And that should make sense because we see an intercept of 100, and we see that this line is lined up at 100, and that that the effect of B given by W, right? So I'm multiplying B by W. B is mostly being multiplied by 0, right? With some little skew, or not, I shouldn't say skew, but spread around 0. Okay, and so now that spread is represented in a couple of ways. So one, there's a solid band here of gray, and this is representing, what did we put? Oh, I don't think I put, so I think the default setting is an 89% credibility interval here. So I guess I probably could have made it a little bit different. In fact, I'll do that here. And then these squiggly lines, these are, again, drawing samples from the prior distribution that we defined, and it's looking at possible trajectories that, examples of possible trajectories that the prior distribution expects, right? So we see some kind of wild possibilities here. So anyway, so this is what the prior predictive distribution looks like, okay? And now we're asked to modify the prior distribution for, I think basically just for W, and see what that does to the prior predictive distribution. And so that's what we're going to do here. So this is the exact model as what we saw above, okay, and that's the prior predictive distribution that it produces. And I'm going to change two things about W, okay? So maybe the first thing that we'll do is, instead of having it be 0, I'm going to change that to 25, and we'll just see what happens to the prior predictive distribution. Code. Okay, and you see that the prior predictive distribution has shifted north, right? It's shifted north to about 125, which is A plus W here, okay, with some band around it, okay? So that should be easy to understand what has happened here. So I'm going to take that back to 0, okay? So that will, when I bring that back to 0, that will shift the prior predictive distribution back down to where it was originally, which just happens to coincide with the data. But now I'm going to take the standard deviation of W, and first let's increase it and just see what happens. Okay, and so now all of a sudden we see that the credibility interval is very wide. Why? Because the values of W that are being entertained by the prior predictive distribution are bigger, right? And so we're going to see a bigger spread around the median. But notice that or I should say the mean, but notice that the mean line really hasn't changed that much. It is a little bit wiggly, but the mean line really hasn't changed. It is the possibilities around the mean line that has really changed, okay? And so now if I really narrow this back down, so instead of being 10, we'll go down to 2. So again, we've already seen what a standard deviation of 10 for W looks like in the prior distribution. Now if we bring that instead to 2, we have a narrower band. Let's see if we can really, let's take it down even more just to make the difference a little bit more noticeable. Okay, so now we have a narrower band. So it's noticeable. So we see a couple of things. So with the gray shaded region, we see that this touches about 120 and 80 or so, and we're just inside of that with this gray band. And then also look at the lines, the extrema of the possible lines. We see two things. One, we see that the extreme of the lines tends to be lower than for the first prior predictive distribution, but also they aren't as wiggly, right? So why aren't they as wiggly? Well, it's because each W value, as we march along the different knots, is more likely to have a much smaller value that B is being multiplied by. Remember, B are these basis spline values that are kind of curving the line up and down. And so if W is small, well then B is going to be small. And so as we go from knot to knot to knot, all of these knots are more likely to be close in value. And so you're not going to get these really wiggly lines. Okay, so that is it for this one.